this lecture we will learn about what is known as birthday paradox. Okay, so, here is the question, suppose you have let us say 30 people in a room, what are the chances that 2 of them share their birthday? In other words, we can ask the following question, we describe 2 events and you have to guess which of these 2 events are more likely. So, event A is that 2 people among this 30 share their birthdays. And the other event is the complement of this event, that is no 2 people in the room has the same birthday. Which of these 2 events is more likely? Since they are the complement events, one of them is going to have probability greater than half, the other one is going to have probability less than or equal to half. Okay. We want to know which one is more likely. Think about it for a minute. So, we need to model this problem carefully. So, let us first model the problem carefully. So, there are 365 days in a year, we will ignore leap year for the moment, and each person is being randomly assigned a birthday. That means, any day is equally likely to be the birthday of any person that is there in the room. So, under this assumption, how do we compute the probability that 2 people share their birthday? 2 people could share their birthday in many different ways, like 3 people could have the same birthday, 30 people, all of them could have the same birthday, 15 of them could have one birthday, and let us say the remaining 15 could have another day as their birthday, and so on. It is a very complicated thing to count, but the complement event is rather easy to count. So, we will basically count the complement event and based on that determine the probabilities. So, we could think of it this way, there are 30 boxes, okay, corresponding to people, and each box you put a number, okay, and this number could be any number from 1 to 365, and each number is equally likely to be chosen to go into the box. Another way of thinking about the same thing is you have 365 boxes and each person is being put into one of these with equal probability, and we want to compute the probability that there is a particular box with 2 people. Okay, they are essentially recasting the same problem in different ways. Okay. So, we are interested in no 2 people going into the same birthday. Okay. So, how many ways can that be done? So, there are 30 people. So, if we want all of them to have distinct birthdays, we should first choose 30 days, and for these distinct choices of 30 days, we can assign any of the 30 people to any of the 30 rooms chosen. So, 365 choose 30 is a number of ways of picking birthdays, and once you have picked the birthdays, so let us say these are the days we have picked, we could either assign the first person here and second person and 30th person here, or any permutation of this 1 to 30 for these rooms chosen or for these boxes chosen. Okay. So, 365 choose 30 into 30 factorial is the total number of ways of assigning the 30 people in the room to 365 days, so that no 2 people are assigned the same day. Okay. Okay. Once again, we first choose 30 days. So, let us call this as D1, D2, D30. Let us say these days are numbered, I mean they are in the increasing order. This is D1 is the first day, that might be let us say Jan 30th, this could be April 1st and this could be December 18th and so on, okay, but they are in the increasing order. So, these 30 days were chosen and now we have to assign people to these days. These 30 days could be chosen in 365 choose 30 different ways, 365 C 30, those many different ways. And once these days have been picked, who gets assigned Jan 30th as birthday? Well, that can be decided in 30 ways. Who gets assigned April 1st as the birthday? That can be decided in 29 ways. So, there are 30 factorial ways of assigning birthdays to people. Okay. So, the total number of arranging people, so 30 people, so that no two of them share their birthday, this is going to be equal to 365 choose 30 into 30 factorial. The entire sample space, that is the total ways of picking us, the first person could have any of the 365 days, the second person could have any of the 365 days into, so there are 30 such people. So, total size of the sample space is going to be 365 raised to 30. So, probability of the event B is going to be 365 choose 30 into 30 factorial divided by 365 raised to 30. We can try and simplify this. This is just 365 choose 30 will be 365 factorial divided by 30 factorial into 335 factorial into 30 factorial into 1 by 365 raised to 30. So, these cancels and whatever we have here is the falling factorial. So, that is going to be, so 365 into 364 all the way up to 336 would be there above, because all the other terms will cancel with the denominator 335 factorial, and then there are, so these are 30 terms and there is another 30 terms which are all 365. So, the first term is 1 by 1, that goes away, the remaining is 1 minus 1 by 365 into 1 minus 2 by 365 into 1 minus 29 by 365. Okay, there are 29 terms, the first term being 1 by 1, that is vanished. Okay, so, this is the probability. Now, that is a difficult thing to compute, but we can see this answer in yet another way. We want no two people to share their birthday. Well, the first person, whoever it is, he can be assigned some birthday, there is no clash, and the second person, if his birthday has to be on a different day, that could be done in 364 by 365 days, or that one out of this 365, that birthday cannot be chosen, that is this 1 minus 1 by 365. Now, once the first two people have been assigned birthdays, there is a 2 by 365 chance that the third person might share the birthday. The probability that that does not happen is going to be 1 minus 2 by 365. So, that is the telescoping product. So, 1 minus 1 by 365 and 1 minus 2 by 365 all the way up, there are 29 terms in this, and that product will be the probability that no two people share their birthday. Now, we need to estimate this, and think of this as a balls and bins problem. We had 365 bins and the balls were people, and we have to throw them into these 365 bins so that no two people share the same birthday. So, let us say we have m people and n birthdays, and we want no two of them to share the birthday. So, this could be done in 1 minus 1 by n into 1 minus 2 by n all the way up to 1 minus m minus 1 by n. Okay, this will be the total probability that no two people share their birthday. Okay, so, we can call that as probability of B. We want to estimate this. So, if m is smaller than n, then 1 minus m minus 1 by n, or this can be written as, this is approximately, or for small values of the numerator, this can be written as e raised to minus m minus 1 by n. Okay, and it can be done for all the, not just for this, for any of these terms, they can be approximated as e raised to minus m minus 1 by n. 1 minus x is approximately e raised to minus x for small values of x. So, when x is equal to, let us say, j by n, this is approximately equal to e raised to minus j by n. Okay. So, the probability of B is going to be the product I going from 1 to m minus 1, or let us say j going from 1 to n minus 1, 1 minus j by n, and this is approximately product j going from 1 to m minus 1 e raised to minus j by n, and that is going to be equal to e raised to minus summation j going from 1 to m minus 1 j by n, that is equal to e raised to minus m minus 1 into m by 2n, which we can approximate as e raised to minus m square by 2n. Okay. So, in the general situation, what we have is probability of B is equal to, is approximately equal to e raised to minus m square by 2n. We want to know at what threshold does, what is the number of people that we should have in the room, so that the probability that two people have their birthdays on the same day is going to be at least half. Okay. So, in other words, that threshold will happen at the value where PB is equal to half. So, if we equate this to half, so we want e raised to minus m square by 2n to be equal to half. That means minus m square by 2n is equal to log half, okay, or m square by 2n is equal to log 2. So, m is equal to 2n log 2 under root. Okay. So, if m is under root 2n by log n, and for this you can see that m is significantly less than n, because it is only root of n log n, 2 times the root of n log n. So, for m equal to this value, the probability will be approximately half. Okay. And when, so m is equal to 2n log 2. Okay. And when you plug in n equals 365, you can see that the value of m that you will get is something like 23. The rounded off to the integer, it is 23. So, what it means is that if you have 23 people in a room, there is a 50% chance that two of them share the birthday. Although the total number of birthdays are much larger than 23, it is something like 365. By having just 23 people in the room, we have a significant probability, that is a 50% chance that two of them will share their birthday. Okay. We will stop here. and we will learn about tail bounds in the next week.